Okay, so for Charles' law, we have, as you can see on the little equation here, okay, and by the way, all of the ones today, the direct relationship is very evident with the way the equations are set up, right? So you kind of see like a fraction and a fraction, fraction and a fraction. If you flip the page over, you'll see fraction and a fraction. So they all look similar, which is why usually you can learn all three of these at the same time, because then once again, it's going to come back to you got to be able to look at these units and pick out what the variable is, and then you can figure out which law you're actually dealing with, right? But they're all calculated the same way. And so I'll kind of go over that in just a second. But for the first one that we're going to be relating volume and temperature. Volume and temperature. It says the volume of a fixed mass of gas at constant pressure varies directly with Kelvin temperature. Okay, so a couple things I want to point out. Here is that funny little saying, fixed mass of gas and then constant pressure. So if you remember from Thursday or Friday when we learned about Boyle's law, what we saw was that fixed mass was talking about the variable n, which is our moles of gas. So what we're saying is that we don't care about them for this one, right? It's a fixed mass, meaning that one's not going to vary. Constant pressure tells me we're not going to worry about pressure changing. We're going to focus in on volume and temperature, okay? I highly recommend that you kind of just focus in on this setup and not worry about the flat setup, because this one looks very similar to Boyle's law, except that it's not 1, 1, 2, 2. It's 1, 2, 2, 1, right? So I'm going to go ahead and cross this one out, because I think we're all better off just plugging into this setup right here. Now, when you go to actually solve this, so we had for Boyle's law that thing where we simplified and then we divided by another number. For this one, we're going to be looking to do, you probably learned it in math class. I've heard butterfly, crisscross, proportion. Somebody today just told me baseball. So you would go diagonal, and then whatever is left over, you're dividing it by, and it looks like a baseball bat with a baseball. So I don't know, whatever you have learned. So if you are someone who, all of those, I just said that, and you're like, I have no idea what you're talking about, then please, please, please just make sure you are doing it the same way that I am. That way I can help you, all right? Because I'm not here to really teach you how to do proportions and stuff like that. It is a very useful skill, though, okay? All right, so we're going to have that set up. All right, the other thing that, before we get too much further down this page, this whole Kelvin temperature. So I want to talk to you guys about that. I'm putting a cloud around it. Kelvin temperature. It is super, super important, okay? In my poor morning classes, I had skipped over this and then didn't realize it till today that it was super important. I think I just forgot for a little bit. So let's talk about why Kelvin temperature is super important. What do we know about Kelvin? Where does it stop at? What number does Kelvin temperature stop at? Does it go negative? Okay, does Celsius go negative? Celsius does, but then we would add 273 to get everything in Kelvin. So do we ever go below 0 Kelvin? No, all right? So Kelvin, it's called absolute zero. That's because it's an absolute scale. If you've ever heard of absolute value, it keeps everything positive, okay? So this absolute scale will keep us from going below 0, so we'll never hit 0. So that allows us to avoid any dividing or multiplying by zeros. It also allows us to avoid getting any negative volumes and pressures, which is also non-existent, all right? So it is super important that when you're given a temperature in Celsius, that it gets converted to Kelvin for your gas laws, okay? Very, 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 very important. All right, so now looking at this graph, this one looks very different from what Boyle's law was. All the rest of these graphs are going to be this positive constant slope. And you can see that. If you turn the page, you can kind of see that that one's going to look that way too. All right, so what we're seeing here is increasing temperature will increase volume, or decreased temperature decreases volume. So that means that these things are directly related. Okay, as one increases, the other increases. Okay, so not inversely related, they're directly related. Now let's put it in the common sense terms, okay, or common language terms here. What is another word that we have used for volume up on the board? Well, milliliter is the unit, but space, right? So we're talking about how much space this gas has taken up. And temperature, what is the thing that we're going to picture in our heads? Speed. Good. So space and speed. So what we're thinking of is if these things are going faster, they're going to expand a balloon out, versus if they're going really slow, they're not going to be pushing out, they're not going to be spreading out as much. Okay? So space and speed directly related. As I speed up, I increase the space needed. You can be thinking of balloons when you're thinking of changing volume. Okay? All right. So now let's go ahead and look at our first example. We don't have to talk this much for the rest of them, right? They're all very, very similar. So this one says, a sample of helium gas occupies a volume of 100 milliliters. So that is my volume 1. At a temperature of 293 Kelvin, that is my temperature 1. Okay? So you notice I'm continuing to do what we did for the Boyle's Law. Label, label, label. All right? Make sure you know and you're recognizing those units at the end. All right, so we have temperature 1. What volume would the gas occupy? So what is volume 2? Okay, that's who I'm solving for. If it was warmed up to 330 Kelvin, that's my temperature 2. So both of these are already in Kelvin, so that's good. We don't have to convert anything. We're already in that absolute scale. So now we're just going to plug and chug. So we have our volume 1, which was 100. So I'm going to go ahead and put 100 divided by, and then we have temperature 1, which was 293. Okay. I'm going to set that equal to volume 2, we don't know. So we're going to just write V2 over 330 Kelvin. Okay. So now we are set up to kind of start calculating this. So I told you we're going to be diagonally multiplying and then divide by the 1 left over. Okay. So if we were to diagonal multiply these, then you're going to be left with the variable in there. So let's go the other diagonal direction. So you're going to pick where the 2 numbers are. And that's going to be who you are going to multiply together. Okay. And then you're going to be dividing by whatever number was left over. So this is where a student told me that it looks like a baseball bat hitting a ball. And I was like, I've never been told that before. It was interesting. So so if that helps you remember what to do, that's going to be what it is. All right. So we're going to multiply. When it goes to typing it in your calculator, if you're using our calculator, you can put it all in one step. If you're using your phone calculator, you're going to want to do it in multiple steps. So I'm going to multiply 100 times 330. So if you're doing it on your phone, you're going to push equals, and then you're going to push divide 293. If you have one of our calculators, you can put it all in one step by using those parentheses. Okay? So when we do this, so 100 times 330 divided by 293, I get the answer 112.6. And I know that I'm solving for volume, so it's liters or milliliters. I look up at the problem. We used milliliters to start with, so we're going to end with milliliters. And that is your answer. Okay? Hopefully that wasn't too bad. Okay? So that right there, that's Charles' law. Okay? All right. So the next one, Gay-Lussac or Montan's law. This one is going to be relating pressure and temperature, so P and T. So this says the pressure of a fixed mass, so there's that funny little idea of we're not going to worry about moles at a constant volume, so we're not going to worry about volume, right? But we are going to relate pressure, and it's going to be directly related to temperature, and there's that Kelvin thing again. So once again, it's going to be super, super important that we are on that absolute scale So anytime we're in Celsius, we have to convert to Kelvin. Okay, and unfortunately, our examples don't make you do that, but you're asked to do it on the practice. So just make sure you're very careful with that. Okay, it does make it makes a difference. You're going to add 273. So Celsius to Kelvin is adding 273. All right, so what we're going to see here is the equation looks exactly the same with the fraction looking thing. Okay, so P1, T1, P2, V, or P2. So I'm going to cross this one out just to not confuse us. All right, and then we have our graph is showing that direct relationship, so a constant slope, positive slope. So it says as temperature increases, pressure increases, or as temperature decreases, pressure decreases. So therefore, these are directly related as well. I wrote that very silly. Is directly, sorry about that. As one increases, the other increases. Okay, all right. So when we're talking about the picture that we're going to have in our head, okay, for pressure, what are we thinking for pressure? What's the common language, huh? Well, we know it's P, but what word are we thinking? Collisions. So we are thinking collisions. And once again, temperature is speed. So what this is saying is if I go faster, more collisions, right? So if I were to tell you guys to get up, walk around, you're not necessarily going to hit each other. If I said get up, now everybody run different directions, you're probably going to hit somebody accidentally, right? So you increase that speed, we increase collisions, all right? All right, so that's the picture that you're kind of coming up with that. And I forgot what I was going to say, so we're going to keep going. All right, so example, we have a tank of chlorine gas at 298 Kelvin. So I'm going to go ahead and label that T1 because Kelvin is temperature. I should have asked you, my bad, but Kelvin is temperature. And 1 atmosphere pressure, so this is P1, is heated to 400 Kelvin. There's my temperature 2. So what is our new pressure? P2. So we're solving for P2, okay? Looking at my two temperatures, they're both in Kelvin, so we are good to move forward. But make sure you take that extra second to say, okay, if one of them was in Celsius, you've got to change it to Kelvin first, okay? All right, now plugging in, we're going to just kind of plug into the equation that's over here. So we have P1 over T1. So I have 1.00 divided by 298. I'm going to set that equal to P2, which I don't know what it is, over T2, 400. Okay, so with that, you're going to get your little crisscross thing or your baseball bat, whatever you want to say. Okay, so I'm going to take those two numbers, I'm going to multiply them together, and I'm going to divide by the leftover number. Okay, so what that's going to look like is we are going to, sorry, I realized you can't see that very well. There you go. So what that's going to look like in my calculator is I'm going to have 1 times 400, and then I'm going to be dividing it by 298. So 1 times 400 divided by 298. So I got 1.34. What are the units that I'm going to put for this? Look at your problem. What did you say? ATM. But yes, yep, ATM. Good. Atmospheres. Nice. All right. Oh, whoops. That was a big box. All right. So, you know, just kind of like the proportional reasoning that we were thinking on Monday with Boyle's Law, we were like, we had to predict at first whether we thought it would increase or decrease. So here we saw that temperature was going up, so we predicted that this one would go up, and that's exactly what it did. Here, temperature went up, so we're predicting that pressure goes up. It did. Okay, So proportional reasoning is not going away. Make sure you're still able to kind of look at things that way. Do you guys have any questions for me so far? All right, we're going to flip the page over then. Here's our last law for the day. So I kind of told you we were going to go through all three of them. And again, it's because they are so similar. You're better off, learning all three, knowing that they exist, and then when we go to do our practice problems, really, really, really force yourself to sit there and figure out which variables you have, and then it's just a matter of plugging them in the same way, okay? All right, so let's finish this up. So the last one that we're going to talk about today is Avogadro's law. So for this one, we are relating moles, so that's our lowercase n, and volume, V, okay? All right, so this says equal volumes of gas at the same temperature and pressure, so that means that we're ignoring temperature, we're ignoring pressure, contain equal numbers of molecules, right? So it's kind of a silly way to say it because it's kind of been the same way every single time, and then this one we're like equal, right? So what they're saying though, okay, we do have our same setup here. We're going to cross this one out to not pay attention to it. It is a direct relationship, okay? So we know that they are directly related. As one increases, the other increases. Molecules, and that volume that it takes up. Okay, so in our common language terms, okay, what we're saying here for moles, this is the first time that we're seeing that one. So that one is amount, right? So how much stuff is there, and volume is how much space it takes up. So the best way to think of this one is definitely going to be the idea of a balloon. Okay, it is as easy as this. If I blow more air into a balloon, it'll be bigger. Right? Isn't that common sense? That's like common sense to the finest, right? So you guys have all experienced Avogadro's law. You just didn't realize it. And so if you blow more air into the balloon, it takes up more space. If you blow less, it'll be a smaller balloon. Okay, is that a whole idea? All right. So, direct relationship, we are saying if I blow more in, it's going to be a bigger balloon. All right, so the example says a sample of helium has a volume of 8.50 liters. So there's our volume 1. And contains 0.6 moles of gas. That's N1. How many moles of gas, that'll be N2, would be required to make the volume 10 liters. So what this is saying is, hey, if you want a super huge balloon, how much more air do I have to blow in there? Okay, that's basically what they're saying. So, and then we had to put in the part where it said temperature and pressure remaining the same, so we're going to ignore those. All right, so let's go ahead and plug in this last example, and then we will be done with the notes part, okay? So, you can see we put V over N, V over N. So I'm going to go ahead and go in that same order there. Okay, so V1, 8.50, all over N1, which was 0.600. I'm going to set that equal to V2, which is 10.0, divided by N2. Okay, so this setup is just a tiny bit different in the sense that we're not diagonally going this way, right? That's not where my two numbers are. Now these are my two numbers. So it's still going to be the same exact idea. We're just going to take these two, we're going to multiply those, and then we're going to divide by the leftover number. Okay? So multiply diagonal and then divide by that leftover number. So we're going to have 0.6 times 10 divided by 8.50. Okay, so 0.6 times 10, push equals, divide by 8.5, and I got 0.71. And what are the units for this answer? No, not N, not liters. Remember, units are the things that go after the numbers. It is moles, yep, good, okay? So we're going to put moles. So you weren't wrong for saying N, but that would be the variable and not the unit. Oh yeah, we were going to go to that. I forgot to do that. Okay, so real quick, flip, because it's already closed, flip it all the way over to the front. I meant to do this with last period. I'm going to have to remember to do that with them tomorrow. So here, the units. Let's go ahead and write in these units so you have something to study. Okay, so this goes with that whole list that I made you guys do. And this way you'll be able to kind of look at that and possibly answer these a little bit better. So for pressure, the units that we have atmosphere, we have millimeter mercury, we have torr, and we have kPa, kilopascals. Okay? You might see PSI, but most likely not. Not from me. Okay? So we're just writing in those. Which two are the same? The millimeter mercury and torr. Yep. These two are the same exact unit. Okay? Because torricelli with the barometer, millimeter mercury. Okay. All right. All right. So for temperature, what were the two units that we got to see about temperature? Okay, Kelvin, and that one is the one that you have to be in, right? So I would put a star next to that one. And then degrees Celsius. Good. Okay. All right, for moles, this one's the easiest. We'll just put MOL. Moles. Okay. But we do recognize that it can be in grams. We can just convert it to moles, right? So moles with the idea that grams is an amount as well, right? All right, and then finally volume, we've seen milliliters, which is equal to centimeter cubed. So just in case you see that, and liters. Okay. So milliliters, which is equal to a centimeter cubed, and liters. Those are the units that you're looking for to decide that you have volume. Okay. All right, so now comes the challenging part. You can flip it back over to where we just were. Those practice problems. I'm gonna put a timer on for 2-3 minutes. I don't mind if you help each other a little, but what I need you guys to figure out is what variables you have, and maybe not necessarily telling me what the name of the law is, but what is the setup? Like, is it the one with volume in moles? Is it the one with volume in temperature? Or is it pressure and temperature, okay? So looking at that, you can kind of just write out what each of the little equations are. And then if you feel ready, you can go ahead and start calculating the answers to these, just so you have them to check. It's going to be 745, 316.7, and 5.63. So I would say as soon as you get those three done, then you can go back to work on the Schoology assignment. Otherwise, I'll probably hand you guys the paper, or we'll start that movie. Okay? All right. Cool. You guys have any questions for me so far? No? Okay, so I would make sure you can do these three. Okay? Yeah, I would.